Okay, so let's draw and do the example carbon Cl2 F2. And if you look at experiment 10, the partial Lewis structure is already given to you. But if we go through, let's go through and generate the Lewis structure, the 3D model, and determine whether or not this is a polar molecule. So we go through, we know that carbon, there's one of them, and it is in group 4, so it has 4 valence electrons. We know that the chlorine, there are 2 of them, and they are in group 7, so each contributes 7 valence electrons to the molecule. With the fluorine, we know that there are 2 of them as well. Each have 7 valence electrons, so 14. And when we are done, we know we need to have 32 valence electrons drawn. So we look at this molecule, and the second step is to determine what is our skeletal structure. So we know that it's generally written first, the central atom, so we know carbon is in the center, and we're surrounded by the terminal atoms. So I will put my chlorines here, and my fluorines here. So with this, I've done step 2. The third step is to draw a single bond from my central atom to all of my terminal ones. So I draw single bonds. So step 3 is done. Step 4 is to give all of my terminal atoms an octet, and I look and I see I have fluorines and I have chlorines, and they are not an exception to the octet rule, so I know that they all want 8. So I give them 8 valence electrons, and again, remember, if you draw a straight line, it's equivalent to 2 dots. So if I continue this, I give all of my terminal atoms an octet, and I look and see, okay, how many of the 32 total have I drawn? And if you count them up, I've drawn all 32. So I have to check, does everything have an octet, including my central atom? So I know all of my terminal atoms have an octet, but does my central? And I see that carbon indeed has 8 valence electrons. So this is the Lewis structure for this molecule. Now, in terms of a 3D model, we see that there are 4 regions of electron density around the carbon. Because remember, with 3D models, that's what we're concerned with. And I know that that narrows it down to 3 possible geometries. But I have to look what kind of regions are around that carbon, and I see that they are 4 of the bonding pairs. So I know that my geometry is tetrahedral. And all of my bond angles are going to be 109.5 degrees apart. Now, if I go to draw the 3D model of this molecule, I know that for tetrahedral, I have my central atom with 2 bonds in plane, so I draw them straight lines. I know one is coming out of the plane and one is going behind. So for this molecule, I would have carbon with 2 in plane, one coming out and one behind. So I stick my molecules in, my terminal atoms, and I have the chlorine, and we'll stick the chlorine here, fluorine, and fluorine. Now, in order to determine the polarity of this molecule, okay, if we only considered the Lewis structure, we could look at it and say, okay, this has polar bonds. We know that carbon and chlorine and carbon and fluorine do not have the same electronegativity. Therefore, there is a difference in electronegativity. Those electrons in the bond will not be shared equally. So we will generate a dipole moment. Now, when we have polar bonds, the problem is that it can either be a polar molecule or a nonpolar molecule. So it doesn't help in the way of determining what the polarity of our molecule is going to be. So then we have to look at our molecule and consider, do I have a net dipole moment? And if you look at just the Lewis structure, I gave you those simple ways in the third example of how to determine whether or not you have a net dipole moment. So the first thing you have to look at is there a lone pair on the central atom? And you see, for the carbon, no, there is not. So you keep going. And if we're looking at the Lewis structure only, we say, okay, next question is, do we have a different atom bonded to the central atom? And you see, yes, we do. We have 2 chlorines and we have 2 fluorines. But if you look at the Lewis structure, it kind of looks like they're canceling themselves out. So this net dipole moment is going this way, which would cancel this one going this way. Same thing over here. We'd have the carbon-fluorine. This net dipole moment would cancel this one over here to the right. So even though they are different, they kind of look like they're canceling themselves out. So you think, oh, they're canceling. That means that we have a nonpolar molecule. But remember, you always have to consider the 3 dimensions. So if we look at the 3D molecule, what you can see is that these 2 will be the same in terms of dipole moments, and these 2 will be the same, but given the 3D molecule, the 3D structure, you know that they do not cancel themselves out. So this would end up being a polar molecule. So one of the things that you have to be careful of is you can't just look at the Lewis structure, because sometimes you have to consider the entire 3D molecule. So make sure when determining polarity, whether or not you have a net dipole moment or not, you always at the end consider what the 3D model looks like.